So what we left off with was the idea that benzene was nucleophilic, and benzene is capable of going after electrophiles. And we built up a collection of reactions in which we added things to the benzene ring through a substitution process. We've added bromine, nitro groups, stuff like that. And looking at the exam scores, for most people, that was well understood. People seemed okay with that, differentiating between an ortho-para director and a meta director. What comes next is more of it. It's more of the same stuff, but maybe deeper in the sense of we've already got one group on there, we've got two groups on there, where does the next group go? And this becomes more useful because now we're talking about polysubstituted benzene rings, which are more realistic in terms of uses. I get through this today. I get the exam back this morning. I send you an answer key out when I get back to my office. And then we're into chapter 20, and chapter 20 is huge. I've got 70-odd slides for chapter 20. It's a really big chapter on carbonyl chemistry. So looking at the exam scores and comparing it with last year, it's almost identical. The scores are almost identical in terms of averages. Looking at the average for the next test, it goes down by 15 points. Right, there's a huge amount of material to come, so we have to keep on this and we have to keep pushing. So recitation this week, I'll be going over the exam a little bit. I'll be going over the benzene stuff to make sure everybody's happy with it, so we move into the more useful stuff. Now, we think about putting pieces onto a benzene ring. You have to think about the order that things need to happen in so that their directing effects go correctly. In the sense, in a molecule like this, if you put the bromine on first, where would the nitro go? Ortho-para. So you don't want that. So maybe you put the nitro group on first and then you brominate. So the directing effect of the first group plays a role in where the next group goes. And then you can get some very efficient syntheses in how to put these molecules together. So what we'll do for the first few minutes today is to get through some of this stuff in terms of directing effects and also manipulating the group outside the cycle. Maybe you put a methyl group on there and you want to send something to the meta position next. You can't do that with a methyl group. You have to manipulate the methyl group and turn it into a meta director. And that can often be done by simply oxidizing things. So this slide is a nice summary of some of the external manipulations you can do with the benzene ring systems to be able to change the directing effect of the group that's there. So if you start out with the nitro group here, we know it's a deactivating group, we know it goes slower than benzene, but we can make it react, and we can make it send a group to the meta position. So if that's what you want, great. Start with the nitro group. But if you want something which has a nitrogen at the top, and you want to put something else at the ortho and para positions, you cannot do it with the nitro group. There's a limitation there. So what you do is you get rid of the nitro. You reduce it down to the NH2, and we saw chemistry that would do that with a metal and some HCl, and that would get rid of the oxygen and replace it with hydrogen, and that gives you the amino group. Now you can do ortho-para chemistry. There are some limitations to this. It's very difficult to go back from NH2 to NO2, right? You're sort of at a dead end right there. But you certainly can go from NO2 to NH2, and that will affect greatly what happens next in terms of the regiochemical outcome. Moving along to the methyl group over here, this is ortho-para directing because it stabilizes the carbocation if some of it forms at that place where the methyl group is next to. But if we want to send the next substituent into the meta position, we might change it to a carboxylic acid. And between now and the end of the semester, an awful lot of the chemistry is carbonyls. It's aldehydes, ketones, and carboxylic acids again. And benzene kind of ties this together. Benzene is a nice transition from the simpler stuff we've done into the more sort of biological polymer type chemistry we're about to do, using carbonyls as functional groups and linking groups. And you'll see in recitation that we can really go lots of places now. If you think about one of these problem sets that are out there, there's a 37-step synthesis. You've already done 8 or 9 with those roadmap problems on the exam, so you're not that, these aren't that difficult. How do you get 37 steps? Well, you add the benzene chemistry to the SN2 chemistry to the benzylic chemistry to the stuff that's about to happen, right? And it all adds up, and you can start to make some interesting molecules. So again, this chart is worth a look. If you look at the bottom down here, if you put the acyl group on through Friedel-Crafts acylation, your next group will not go ortho-para in the major product. It will go meta. If you want it to go ortho-para, you have to change the carbonyl into something like an alkane. You have to reduce it down. Now, there is more sort of flexibility here because we already know carbonyls will do Grignard chemistry. We know that alkyl groups here with the benzylic position can do brominations. So there's more flexibility there than you might have with a nitro group and an amino groups. And then at the end here, but some subtle things. We have talked about this, and it's something that you should be aware of. If you take something like an alkyl with 3 protons at the benzylic position, you can replace each of those hydrogens sequentially by doing radical halogenation, and that will give you a CBr3. And the electron withdrawing ability of that CBr3 or CCl3 or CF3 should be understood now that it will change the outcome in the next step because it will be a meta director and deactivating because it's electron withdrawing. So the vast majority of people who are passing the class, which is the majority, which is great, seem to have a handle on that. So when we put this together with the next step, it should just be a bit of fun. So here we go, some sort of challenges. How do you make polysubstituted benzenes? Well, you're going to use the same chemistry. There aren't really any new reagents here. It's just using them in the right order, coming up with sequences that make sense. So here's the job. We want to make this material. This has some use. And we can see now that the NH2 group at the top could come from an NO2 group. And we'll have to do some retrosynthesis. So in recitation, I'll show you how to do that in more detail. That NH2 is brought into that molecule typically using NO2. But then you have to get rid of the NO2 to make this product. And the Cl here is brought in under the classic conditions of Cl2, AlCl3. So putting those groups on is not that difficult. The decision you have to make, and what is tricky and kind of fun when you get it, is when to do what. So if I were to put the chlorine on first, would that be a good thing or a bad thing? It wouldn't make any sense, right? Because that's an ortho-para-director, and the next group would have to go in the meta position. If I were to put the nitro group on and then reduce it to NH2, is that a sensible thing to do? No, because NH2 is ortho-para-directing, and you want this next group to go in the meta position. So you would do this in a certain sequence. You would do this by putting on the nitro group in the chemistry at the bottom and make this into NO2, and then you bring in the chlorine, which would have to go to the meta position by default, because meta is better, and then you get rid of the NO2 and turn it into NH2. And what you will pick up as you learn these reactions is the compatibility of the reagents. Often, the reagent working in one part in the molecule doesn't affect somewhere else, and that comes with just experience and practicing more problems. So you can get away with these types of reactions in terms of good yields and good processes. So there are some sort of caveats here. There are some sort of issues where things just don't work. You've got to be aware of some of these things. If you try to do a nitration reaction on aniline, aminobenzene, it doesn't work. It does not give you that outcome. Any ideas why? Any ideas why this type of molecule is not going to give us what we're looking for when we mix it with nitric acid, sulfuric acid? What's the hint there with the lone pair? It's a base, right? It's a base. So if you were to put that molecule in the presence of an acid, it would react as a base, and you'd protonate that thing, and all of a sudden its directing effect is lost. So that doesn't work. Now, if you move down to the bottom, we can see here some deactivating groups. We already talked about this one at the bottom. Nitro is pretty much a dead end in terms of alkylations. You're not going to be able to alkylate because the alkyl group or the alkyl electrophile is not strong enough, and so nitro group is too deactivated, and that doesn't work. So there are 2 or 3 issues where you have to be careful to be able to try and put a synthesis together. And the idea now here, delta plus on the carbonyl carbon, is electron withdrawing enough to make an alkylation not work. Some other things will work. You've done nitration, right? You did a nitration experiment this semester? You nitrated methyl benzoate. Yes, no, maybe? Yes, you did. So keep that in mind. You have done some of these things. In terms of nitration of experiments, you've already nitrated methyl benzoate. So that says having a carbonyl at this position is not deadly or going to stop the possibility of some kind of reaction with, let's say, a halogen or, let's say, a nitro group. So you've done that in the lab. Just make sure you recognize that that will react under those conditions, and you can actually do that even on paper and in lab. So with those in mind, you can start to build molecules quite easily. And you can see again, like we've talked about on the Wednesday before we broke up for the break, is that some of these things act cooperatively. Sometimes you have 2 groups on there, which will then send the 3rd group into the same place, and that can be useful. So that's the end of that. Now, you know, I've got dozens of examples out there to practice. I've got plenty to say in recitation for practice, if you like. Office hours, come and ask me if you're not happy with what's going on there, but practice those problems. There's a lot of stuff on the web there. Getting ready for this next exam, which, you know, I always say this. I know it's sort of redundant, but it is more difficult. And I'm just looking at the old scores from the old exams because the scores goes down, and that means it's more difficult. So let's keep up with this and make sure we're on top of it. Okay, last thing to talk about. Really 2 reactions here. Some rather strange processes in which the benzene seems to change role. It seems to swap what it's acting as in the reaction. And we can look at the top and think, well, it's still a benzene derivative. It's got one group on there which is strongly deactivating, and one group which is weakly deactivating. And what we've done here is swap the conditions. The key here is that this is not an electrophile. What can sodium hydroxide behave as? Base or nucleophile, right? Now it seems all of a sudden that we are swapping the role of the benzene ring by introducing it to a nucleophile. Now this only happens under certain circumstances. It only happens when you have strongly electron withdrawing groups in certain places on the benzene ring. So when you're looking for the outcome here and what to think about how it happens in terms of a synthesis problem or in terms of a mechanism, you're looking for certain groups that are deactivating and electron withdrawing. And the most obvious one is the nitro group. This is the most powerful electron withdrawing group that you've seen here. And this sets this reaction up. Okay? You see at the bottom, just to get this started, it does not work in the meta position. That's very telling. That tells you something about the mechanism. All right? We're going to use this nitro group here as what's called an electron sink. Okay? It's some place we can push electron density temporarily and then get it back. And when we get it back, we'll get the benzene ring back. So this is quite different now. All of a sudden now, instead of the benzene ring going after some electrophile, which is what we did for the first half of the, first 2/3 of this chapter, now it's the other way around. Now the benzene is the electrophile reacting with a nucleophile. So this gets a different name. There's a nucleophilic aromatic substitution, and it only happens under certain circumstances. It's fairly obvious to see when this will happen. So now, if this OH group is acting as a nucleophile, we have to decide where it's going to go. It's going to attack on carbon, and it's typically going to attack there for two reasons. Number one, that's the most delta positive carbon out there, right? It's right next to the bromine. Also, it's the best place you can put electron density when you start to make resonance structures for the intermediate. On top of that, what's bromine going to behave as? A leaving group. So that's the only place you can attack where the bromine comes off. And that's exactly what's happened. The Br has been lost, and it's been replaced by the nucleophile. In this case, it happens to be hydroxide. So nucleophilic aromatic substitution. It is absolutely key to have this group there. That will serve as a place to put electron density temporarily in the intermediate to stabilize the intermediate to allow for the reaction to happen. Now, it's key to notice that at the bottom, it doesn't work with the nitro group at the meta position. And the answer will be, in the intermediate for this type of structure, the NO2 group is redundant. The NO2 group is in the wrong place. You can't put negative charge into that NO2 group if it's at the meta position. And when you draw the resonance structures, you'll see why. So getting back into this, here's a mechanism for the successful reaction. Here's how you turn this sort of 4-chloronitrobenzene into the 4-nitrophenol. This is a useful process now. You will do this in biochemistry and later in the future, I would think, if you take that class. You need to have a leaving group, and you need to have a strongly electron withdrawing group in the correct position. It works for orthonitro, and it works for paranitro. It does not work for the metanitro. What is happening is the nucleophile is going after the electrophile. The electrophilic benzene ring now is accepting electron density. It has switched roles from the earlier chemistry. And what we can draw now is something called a Meisenheimer complex after the chemist who discovered these things or suggested that they existed. We can put electron density onto the ortho position by doing this. You can see there's the first arrow. That's pushing some electron density onto the ortho position next to chlorine. And then we can draw a second resonance structure in which we put some electron density next to the nitro group. Now, the example on the exam where you had the CN group next to, you wanted to avoid putting positive charge next to a CN group, it's the opposite here. You want to put negative charge next to a nitro group because it helps stabilize it, because it's electron withdrawing. So all these three structures here are some things that you should be able to draw. They're just negative charge being pushed around different allylic places. The fourth one is key. The fact that you can dump some of that negative charge into that nitro group in that fourth resonance structure suggests that helps stabilize the process. You cannot do that. You'll try this with the meta, right? If you want something to practice, try with the meta. And you'll find that nitro group in the meta situation just doesn't work. You cannot put the charge there. Michael. Yeah, it probably does. Yeah. But you're typically looking for the orientation of the Cl or the bromine being para or ortho to the nitro group. That's key for the electron density being distributed in the right places. Pretty happy with that? Yeah, back into it now. Fourth quarter, here we go. So this is a way of substituting on benzene, which is the opposite of what we did previously. We substituted a hydrogen previously with electrophiles. Now we're substituting a leaving group with a nucleophile. It's quite different. So that's sort of it for that. You will see this in biochemistry later when you put fluorines on here. You use something called Sanger's reagent to identify peptides and things like that. But right now, looking out for nitro group, leaving group, substitution pattern. That's all there is to it. Obviously, once you've done this reaction, you've got some use for these materials. Okay. What is the acidity? What's the pK of that proton? 10, so you can take it off and do a Williamson ether synthesis as we did earlier. All right? If you get rid of the nitro group, you can put tin and HCl, or you can put zinc and HCl, and the nitro group will go to NH2. You can use those materials now as precursors to something else. So you're opening up the playing field by doing this nucleophilic reaction. I'm assuming you're happy with that. We'll find out. Okay. The last thing in that chapter is really a discussion of a remarkable reaction which is used industrially, the Dow process. It's used industrially to make phenol itself. Now, this reaction is something that is sort of beyond the sort of mechanistic things that we've talked about so far. This does not fit well or doesn't sit comfortably initially. And you have to understand that this works and it's viable, but it needs some fairly vigorous conditions. It needs some fairly dramatic conditions here. You can take chlorobenzene, which you can make from benzene by chlorinating it with Cl2 and AlCl3. And you can treat it with sodium hydroxide, and then you heat the crap out of it. All right, 350 degrees C. That's some dramatic sort of conditions. For us chemists, maybe not for the engineers. You can imagine trying to do that in a lab. If you try and heat these two things together, chlorobenzene boils about 180. You're going to have to take some precautions here, right? You're going to have to do it in maybe a sealed vessel. So that maybe can bring in some problems because that builds up pressure. And you have to be careful how you do this, especially on big scale. If you heat this thing at 350 degrees, it goes. If you keep it at room temperature or below 350, it doesn't work very well. So that tells you how difficult this process is to do. And what we're doing here is basically swapping the chlorine for the hydroxyl. Now, if you go back to the previous slide, we did that just now. We swapped the chlorine for a hydroxyl, and it wasn't a problem. But the difference now is the lack of that nitro group. The lack of that nitro group is key here, and it changes the mechanism dramatically. Because there's no electron withdrawing group on that cycle that will absorb the electron density of the nucleophile. The NO2 group is not there. That's why you can't do this at room temperature. If you had an NO2 group right here, down at the para position, you could probably do it at room temperature. So now this is sort of, really sort of dramatic chemistry. 350 degrees C is beyond my comfort zone in terms of, bonds start to break and things like that. But it works. And so what we have to do here is sort of reconcile how we can get rid of a chlorine, and it'll behave as a leaving group, as obvious, and how do we replace it with a hydroxyl? And the answer is it isn't simply this. It isn't the same mechanism that we just talked about, right? It isn't that. And you can prove this quite nicely. There's a nice labeling experiment coming up in which you can prove that this isn't working that way. So otherwise, how can you do this? Hydroxyl can behave as a nucleophile, and it can behave as what? Base. And that's pretty much it, isn't it? We've never seen OH minus be an acid. That's pretty much it. It's been a base or it's been a nucleophile. So within the limits of mechanistic understanding, it has to be one or the other. And I'm telling you here that it's not a bimolecular reaction in terms of the substitution process. It's not a direct substitution. So what is it? Well, let's think about how we can solve this. How can you come up with a mechanism if it isn't as straightforward as one we've seen? You do some experiments. And you try and run experiments that give you some information about where the incoming species and the incoming group, where does it end up in the molecule? Does it always go for that para position? Is it a straight swap? Okay? Is it a straight swap for, let's say, the chlorine? All right? Because if this is happening in a substitution type process, you should only get that product, right? And that's pretty obvious if you only have one substitution on the benzene ring. But what if you put two on the benzene ring? What if you put a methyl group down here? That will change things. If it's a straightforward swap where the chlorine gets kicked out by the nucleophile, you should only get this product. But you don't. If you put that group there and you have now a disubstituted benzene, it turns out you get isomers. And I would hope, since most people are doing well, it's pretty obvious that this species here, this product, cannot come about from direct substitution of that chlorine, because there isn't a chlorine in that position in the starting material. So here's how this mechanism was solved, how people worked it out. So starting off again with some halogen with no extra activating group, no acyl group, no nitro group to absorb electron density, and then treating it under fairly harsh conditions. In this case, NaNH2 in liquid ammonia. So this is not sodium in ammonia. This is not the Birch reduction. This is NaNH2, which is either a base or it's a nucleophile. And we've used it primarily as a base. Well, if you do it with just chlorobenzene itself, you get a straight swap of C-alpha NH2. It's a nice way of making aniline. If you don't want to start with benzene, make the nitro group and then reduce it, you can do it this way. Start with the chlorobenzene and then turn it into NH2. That could be useful in some synthesis. And then, at the end of this, you need to acidify. You need to quench. So the bottom experiment is key. I would put a big asterisk, smiley face, whatever you use to differentiate or to tell, hey, this is important. I would put one there. Because this reaction now is pushing the mechanistic ideas that we've seen so far. Well, it's not a straightforward nucleophilic substitution. Okay? It's not a straight swap. And that can be proved by the fact that there's no chlorine here, yet we end up with a product with an NH2 group there. So it must be something different. And this is quite dramatic. This is quite a cool mechanism, which is, people are happy with it now, but it's quite different. So there's an experiment at the top. Starting off with some material, some labeled chlorine, some labeled material, in which, let's say here, we have a C14, or we have it heavily doped with C13. Something we can see. Where can we see C13? NMR spectra. Right? If you dope something, don't forget NMR spectra, C13 spectra is all about seeing C13, but it's such a low abundance. It's less than 1% in each of those carbons of C13. So if you dope this by putting more C13 there by some synthesis, you could imagine that the signal for this would get bigger. in the C13 spectrum. For that one carbon would get bigger. And then you can follow it by C13. Or if you were, you were a little bit more daring, what about C14? What do you know about C14? Radioactive. Now we're getting to the fun stuff, right? Radioactive. So you could follow that by some trace and try and work out where it ends up. So here's the experiment. You start out with some labeled chlorobenzene. And we're trying to prove the mechanism here. We're trying to show that it's not a straightforward substitution process, and it's more complicated than what we've seen before. This is analogous to having an R group at the bottom. You put a label at the top, and you get 50% of this, in which the label ends up next to the incoming nucleophile, and you get 50% of that, in which the label ends up at the ortho position. So that tells you you've got some intermediate species which has an equal chance of attack from both sides. What does that remind you of 50-50? Racemic. Think about racemic mixtures, right? That was always the idea where something was flat, and you attack it from both sides, and it was prochiral. You ended up getting a 50-50 mixture which was racemic. Now, this isn't racemic because it's all flat. Yeah, there's nothing going on here in terms of racemic stuff. It's not chiral. But it's the same idea. You're going to produce maybe some intermediate species, which is, let's say, symmetrical. And if it's symmetrical, it can be attacked on two different carbons to give you two products that are similar, okay, but the label is in a different place. And here's what's understood as the mechanism now. At the bottom, we've got the chlorobenzene, labeled as such. And we're treating it with this. And this is either a powerful nucleophile or a powerful base. But we've just got rid of the idea that it could be a nucleophile because we don't get, we do get substitution at the ortho position, which did not have a leaving group. There's no leaving group here. So the other role for NH2- is the base. So we can now imagine something happening here where a base comes in, grabs a proton at the ortho position, and forms this. And that should sort of, that's a little bit different. It is a negative charge on a benzene ring. Not in a benzene ring, but on a benzene ring. And you think about the shape of this molecule, you think about the benzene ring being flat, and that sp2 system in the cycle all being conjugated. Where's the negative charge? It isn't in that cycle. It's not part of the pi system. Where is it? It's pointing out from the cycle. Okay, this negative charge, this lone pair, is in a lobe that's 90 degrees from the pi system. So it's unstable. Well, this is an example now where the elimination seems to be happening from not here. It's not straightforward E2 by the looks of it. Right? E2 would involve this arrow going to here and this chlorine breaking off. And is it an E1? It's not an E1 because there's no carbocation. You can't lose that Cl as a negative charge and leave behind a positive on a benzene ring like that. It doesn't work. So the other alternative is a mechanism you haven't seen anything of yet, but we will see it in the next few chapters. This is the conjugate base of that molecule on the left. Okay? The elimination happens here, the slow step happens from the conjugate base. And this is unimolecular in the sense that this one molecule is collapsing. So we'll see this again and again. This is an E1 from the conjugate base. It's a slightly different type of elimination process that you haven't seen just yet. You've seen E2, bases and alkyl halides. You've seen E1, typically alcohols and some weak base or neutral conditions. And now we're looking at E1CB, elimination unimolecular from the conjugate base. Well, that then gives you this. And this is something that should disturb you. You should have nightmares about this thing, amongst other things. What's so odd about that? What's so strange about that? Strain. That looks like an alkyne in a six-membered ring. It is strained. Now, people have done calculations on these things, observe them experimentally. It happens. If you're okay with carbocations, you're okay with negative charge, you're okay with things that exist for a short amount of time, this is just another reactive intermediate. Yeah? It's nothing more strange than a radical. So this benzyne is super strained, and therefore it will react. But this is the only real explanation for how you get that 50-50 mixture of products. We're trying to explain things here, right? How do you get that 50-50 mixture of products where the label ends up here on the original carbon and here on the ortho position? It's only possible if your intermediate is symmetrical. And benzyne, I think, is symmetrical. So this carbon here, chemically, is the same as that carbon, if this indeed is an alkyne. Good enough? This is understood. This is what people believe. Now, with that in mind, that isn't going to last long. You can't stop benzyne, right? Benzyne is on the charge. It wants to react with something. So what you have to think about now is what else is in this mixture. Well, I think I just made ammonia. And I think I've got some ammonia in there, and I've got some other bits and pieces that we can use now to get rid of this triple bond and make it stable again. So here's the second step, or here's the outcome after you form the benzyne. You can imagine this being nucleophilic, going after the alkyne and producing this type of species, this type of charge. Don't forget, and this is probably worthwhile talking about right now, what pH are we at right now? We have NaNH2 and NH3. In the previous reaction, we had NaOH. What is the pH, high or low? High, very high. There is a general saying that in mechanisms at high pH, where you've got hydroxide or bases or nucleophiles, your intermediate species tend to be negative. Negative bases. There's a correlation there. If you think about acidic reactions where you have a proton which is positive, a lot of this to come in the near future, the mechanisms tend to contain positive species, electrophiles, Lewis acids, things like that. So this is the negative one. This is the high pH. Pretty much everything's negative. So I'm going to take a negative charge and attack my molecule and end up with a negative charge to balance it. That makes sense. What about this thing? Stable or unstable? Unstable. It's getting better. It's getting better because you lost your triple bond inside that cycle. That was horrible. But now we need to finish this thing off. And this thing in this reaction, what is happening here? What type of reaction is that? This is why people can't pass my quizzes in recitation. What type of reaction is that? Acid-base, right? What's the simplest reaction we've dealt with and the fastest reaction we've ever dealt with? Acid-base. When I give your exam back, your quiz is stapled to the back of it if you didn't pick it up already. And so many points on those quizzes are lost by people forgetting simple acid-base chemistry. You cannot. So once we get here, we've got a chance now to pick up this proton. Where did that come from? Ammonia is the solvent for the reaction, so you have this in there. And you end up with a material that has the amine group ortho to where the label was. In other words, next door to where the leaving group was. So you want to get something out of this, you want to think, well, we can do experiments quite easily, quite simply, to prove the outcome and to nail down what the actual mechanism is. So this Benzyme mechanism now, this is the odd one. Where did that come from? Because it's not a straightforward substitution because there was no chlorine there to start with. At the bottom, this is the other possibility where we attack at the other carbon, in this case, which has the label. You think about that, chemically it's the same as the one next to it. There's nothing different there in terms of chemistry. So we attack that, we produce a similar intermediate now where the label is actually now still next to the NH2 group, and we end up with this one. So benzyne now is understood to be an intermediate in reactions that involve strong bases with benzene substituents with leaving groups, sometimes at high temperatures. And again, the proof of this is the label or the substitution pattern with the methylbenzene we started with, and that's something that you should be okay with. It's very useful. Well, you all right? Okay. Well, you can use benzyne in all sorts of different ways. We did this experiment in undergrad. It was a lot of fun. You think benzyne's in there. You have to prove it. You're trying to work out why it's in there. And one of the simple experiments you can do is use it as this. You can do it in this type of reaction. This is a Diels-Alder reaction. So what is benzyne reacting as? What's the component there? It's the dienophile. Benzyne is a really good dienophile. So watch out now for benzene chemistry or benzyne chemistry in the Diels-Alder world. You can use it to make some pretty impressive bicycloaddites like that. Simply by adding a diene, of the many of which you've seen, you can use whatever you want, and generating this stuff in situ. In other words, in the flask. You're making it along the way. So you're not adding benzyne as a reagent, you're making it in the flask, and then once it's formed, it's reacting with whatever's present. In this case, a diene to produce a Diels-Alder adduct. So here we can see again the mechanism here for the Dow type process in which we have some leaving group. You're just looking for a halogen, some bromine or chlorine, something like that, iodine, and we can get acid-base chemistry where this is happening at the next position here, giving us the intermediate species, which then gets protonated from whatever solvent you have, and away we go, we have a product. So it's really useful, and it's very different to the first example. This is why I stopped for the exam with just the electrophilic chemistry, because this shakes everything up. It's now the opposite. Okay, hopefully you got lots of rest over the break, because what's about to happen now in this fourth quarter of this game is, it's all going to happen. It's all going to come together. So let's finish this off. Take a few minutes just to summarize that chapter, and then I'll give the exam back and we'll talk about that and talk about what's to come next. You have three mechanisms now in benzene chemistry that are on top of outside the ring. Outside the ring, you've got the benzylic oxidations, benzylic brominations, SN1s, SN2s, at the benzylic position. Here, now, we have three mechanisms in the cycle, in which the cycle, or the 6-electron pi system of the cycle, takes a role, and plays a role. We have seen a lot of this. From what I saw on the exam, most people are happy with that. Okay? Some people still refuse to draw mechanisms properly. They still draw everything backwards, and fine, you'll enjoy taking it again. But most of you are fine with the way the arrow should go. It's a language. We're all driving on the correct side of the road. We're not crashing into each other. So in this case, much of what we did in that chapter was use the benzene ring as the nucleophile and go after an electrophile. And you generated the electrophile E+, and in recitation we hammered on this, and we said, look, all you need to worry about for that reaction is what is E+. Once you know what E+ is, you can just do they're all the same. It's all the same mechanism. And we can see here now resonance stabilization, but look at this. All of the reaction conditions that we used here for making E+, because your job is to work out what's going to happen when. E+ in this case was made from nitric acid, sulfuric acid to make NO2+. What is the pH of that reaction mixture? High or low? Low. Nitric acid, it doesn't get much more acidic than your sort of experience, right? Positive species, protons, positive things, electrophiles, positive things, positive intermediates in mechanisms. So you can see here, there's a positive species. Resonance structures all contain some positive charge somewhere, and that can be identified from the conditions. In the reaction between, let's say, methyl chloride and AlCl3, what is the AlCl3 happening or behaving as? A Lewis acid. What's the clue in there? Acid. Yeah? So again, you can think of it as low pH. All the intermediates are positive. Straightforward. Now, move on to the ones we just did. We have changed dramatically, and the reason I'm hammering on this now, and I'm not being facetious, I'm being honest, being straightforward about this. If you don't get pH the rest of this semester, I might as well teach it in Greek. If you speak Greek, right. If you don't, it's a mess. Because pH really is key now. And as you head into biochemistry, I would argue, Cole, that biochemistry has something to do with pH. Oh yeah. Oh yes, big time. So what I want you to try and get between now and the end of this term, the end of my class, is the thorough understanding of the functional groups and pH and the consequences of having one in the presence of the other. We're going to go do acid-base chemistry again. We're going to do a lot of different chemistry that you've already seen, put it into this bigger picture. So what's changed here? I've gone to hydroxide. What's the pH now? High. So we ought to expect if this general idea of the species and the mechanism should match the conditions, I should have negative intermediates. I should have the distribution of a negative charge if I'm starting with a species that is very basic. And I do. This overall species here is negative. So the nucleophilic substitution process that goes on here is dependent upon having a nitro group there. That's the most obvious example of where this works. And it helps stabilize a negative charge. But in general, as we're heading into the bigger chapter coming up, chapter 20 is huge, if you can recognize the pKa or the pH of the mixture, you have a good idea of what the mechanism will be in terms of the charges of the pieces involved. So hydroxide is a base, it's negative, the intermediates will be negative. At the top, most of these conditions were acidic, the intermediates are positive, like a proton, right? Like an acid. And down at the bottom, this was just a weird one. This is great fun. This is the one in which we just finished off by talking about benzene giving benzyne. What do you need for this? You need a leaving group. You don't necessarily need a nitro group. That can lead to the substitution reaction above it. You need a powerful base. And by that, it could be hydroxide and high temperature. It could be NH2 minus and maybe room temperature, NH2 minus being a much more powerful base. So we can see now 3 possibilities, and your job is to decide which one goes when. So we have a sit-down quiz coming in class next week in recitation. We'll do some of this there. Make sure you're happy with that for that quiz. The quiz is out there for 19 already on the internet, and you should be able to get the homework done as well. So this last slide, I believe this is the last one for the chapter, and then we'll break and give the exam back. This now is the trick or the job to get a good grade in the class or to pass the class for the rest of the term. The chemistry coming up isn't necessarily that more complicated. There's just a lot of it. The chemistry coming up is largely applicable to biochemistry. And I'm teaching this other class, which is the organic chemistry of biological molecules. I spent most of the break writing slides for this class, and it's all carbonyl chemistry. It's all C double bond O, it's all carboxylic acid chemistry. So biochemistry is all based on those functional groups. So the job to do now is to keep up with it and to focus, and so that you come out of this understanding what you're doing. And this type of slide will help for that chapter. What decisions you have to make, how do you make them, and practice. And what I find with, I'm going off on my little rant now, but that's okay. What I find strange is that people can get a 10 on my recitation quiz and then 3 days later get a 90 on my exam. Yeah, what does that tell me? It tells me that people can't do simple acid-base chemistry on my recitation quiz, or they're cramming at the end. They're putting all their effort in the last 2 days. Now, if you're getting 90s, great. If it works for you, great. But for most people, it doesn't. For me, it didn't. And if you want to get B's and A's in these classes and classes in the future, like biochemistry, which is much more difficult, keep up with it. Keep going. Just keep at it every day, and you'll be fine. So here's my exam 2 outcome. And to me, that's pleasing. And I've never taken a statistics class in my life, but it's always fun to go back and look at previous years. So I looked at last year's exam, last year's class, and last year's summary to this point. It's almost identical. I've got almost identical number of people passing and the identical number of people failing. It's just bizarre. That's just the way it is, apparently. So I've got plenty of people getting above 90 on that test. That was great. I thought that was a pretty tough test for the time you had to do it. So I was very pleased with that. A lot of people got above 90. I got a very solid number of people getting above 80, which is a B. And I hope you're listening here. I am not curving this class. I do not have to curve this class because the grades fall out exactly as advertised. The A's will be 90 and above, the B's will be 80 and above, and the C's will be above a 60 up to a 79. You need to be in that range. People down here getting 60s, you get a 60 on my test, why can't you get 70s? I never understood that. Down here, it's not going to happen. Down here, it's not going to happen. And as I said previously, the low, the low wasn't as bad as it has been in the past, but the high was 100, 2 people got 100, and the low was a 39. And the average was average on this one was an 80. That's great for an organic test. Now, to put it in context, after 2 tests, you can start talking about an actual grade, if you like. My average for the class after 2 exams is 78 out of 100. With the next exam coming up, if the trend is the same as in previous years, the average at the end will be about a 74. That's solidly in the C range. There's no need for a curve there. So if you're in the 50s or below, you're not going to pass, right? And you've had so much opportunity to get help and people don't want it. There's nothing we can do about that. Pay for it again, take it again, that's up to you. My average after 2 exams is 99. There are people in this class who are barely dropping a point. There's the competition if you're thinking of anything in the future in terms of professional school or graduate school, and the lows are 39. So I'm going to get the exams back, and we're going to go to recitation. And if you have any questions in terms of my grading, find me as soon as you can. And make sure we're ready to go.